All right. Is everyone hear me okay? Well, you can type yes in the chat window if you want. Awesome, great. Good morning, or good afternoon, good evening. Depends on wherever you are. I see the registry list just now. We have folks join from all over the world today. Some from Seattle, San Francisco, New York, Toronto, London, Berlin, Sydney, and some from India. Well, that's great. Anyway, thanks a lot for joining us today to learn AI. By the way, I'm Bill, today's web host from AI Camp. Before we get started, I just want to do a quick introduction on AI Camp and a few announcements. AI Camp, with the mission of make AI available to all developers, is a global online AI learning platform for developers, engineers, data scientists to learn and practice AI technology. So we're mainly in Seattle and Silicon Valley. We are one of the largest AI technology communities and have local learning groups in more than 40 cities from more than 10 countries. With hundreds of tech lead speakers and more than 80,000 tech engineers in our group, we learn and practice together AI technologies, machine learning, deep learning, data science, so on and so forth. We have hosted more than 500 tech meetups, webinars, boot camps, and workshops, and also a large tech conference as well. As I mentioned, we have AI online tech talks, a few of them coming up next week. So tomorrow we have another tech talk, AutoML from Google Brain team. And next week we have distributed deep learning jobs on Hadoop by LinkedIn team. We also have a couple of AutoML tech talks by the Salesforce team and also NVIDIA team on the deep learning on mobile device. So check our website. We have a lot of, we have regular online AI tech talks. Besides of the tech talks, we also have a crash course online. And for next month, we have a deep learning for developers. This is a 4 weeks long online live crash course. We take the unique approach to learning deep learning by doing project. So instructors will using a few project guiding through to learn the deep learning and building the models and the applications. So it's 4 weeks. Totally is 16 hours, 8 sessions, have some lectures, have code labs, and also we have guest speakers from industry to share. So right now it's early bird promotions. So if you are interested, sign up. By the way, the first session is a free trials. And if you want to speak and share your knowledges and experience in AI at this webinar, you can submit talks to us too. Another announcement is we are building the local chapter program in each of the cities. So if you want to volunteer and working on the building the local technology communities in your city, please reach out to us. We can work together on that. Right now we have more than 40 cities around the world have the local chapter program. Today, I'm very excited to have Francisco to talk about machine learning and deep learning. In this 1 hour webinar, we will tell you how to get started, point you to resources and libraries, and give you some fun problems to get you going with the machine learning and deep learning. A little bit background about Francisco. He is chief data scientist at Catalyst Data Science, and he is also of the 5-day Zero to Deep Learning Bootcamp and book. Francisco works at the cutting edge of machine learning and deep learning training, helping Fortune 500 companies to upskill through intensive training programs and strategic advisories. So formerly, he co-founded and the chief data officer at Spire, a YC backed company that invented the first consumer wearable device capable of continuously tracking respirations and physical activities. Without further ado, let's welcome Francisco. Hi, Francisco. You can start
Hello, everyone. Hi, Bill.
Yes.
Can you guys hear me?
Yes.
Wonderful. Okay, let me share my screen.
Okay.
Get started.
Yep.
Okay. And here we go. Okay. So thank you so much for being here so numerous. I really appreciate the interest for machine learning and deep learning. These are technologies that are truly revolutionizing the times we live in, way beyond what we would have expected even just a few years ago. And so it's really important that you guys become familiar and see how easy it is to get started in those disciplines. So I prepared a little gist with all of the links for today. Become familiar and see how easy it is. There is an echo. Please mute yourself. Yeah. So there's a link. It's bit.ly/ZTDL talks. And there you can find all of the links for the slides and the code that we'll see today. So just visit that link and then we'll you will be able to find other links to the slides and the code. A couple of words about us. I am founder of a few companies. Main one is called Catalyst Data Science, and we do consulting and training, mostly for companies. So we help teams of engineers upskill in data science, machine learning, and deep learning. I also founded training programs such as Data Weekends and Zero to Deep Learning, which is our main program right now. It's a 5 days intensive bootcamp here in San Francisco. It's live and in person, and it basically brings you up to speed with machine learning and deep learning. It's targeted to software engineers that want to quickly transition into machine learning and deep learning. So take a look at it. I'll spend a couple more words at the end of the talk. All right. So you're about to receive a crash course in machine learning and deep learning. And since this is a 40 minutes webinar, I won't have time to go into the details of everything, but I hope I'll give you enough pointers to the relevant libraries, the relevant techniques, the relevant questions that you should be asking when starting a machine learning or deep learning project. Okay. So first thing first, we are going to talk about supervised learning in this talk. Supervised learning is a branch of machine learning, and the other one being unsupervised learning. Given the time restrictions, I think it's better to focus on the easiest of the two, which is supervised learning, which essentially means one of these two techniques that you see here in this slide: regression and classification. I'm sure a lot of you are already familiar with these terms. If it's the first time you see the term regression or classification, let me briefly explain what they mean. Both of them are techniques that connect inputs to outputs. So data comes in the model as input in the form of numbers, and the model tries to predict an output that resembles what we call the ground truth or a label. So in the example to the left, what you see is a regression where we try to predict the average weight of a person based on that person's height. And the red line is the line of best fit that fits the data, the blue dots. Each dot is a person. And that can be used to connect the input, in this case, is just one number, the height, to the output, the weight. And therefore, that's what we call a model. It's a very simple model. It has one feature in input and one feature in output, but yet it's a supervised learning model. The important thing here is that the quantity we are predicting is a number, and that's what makes it a regression. That's in contrast with what you see on the right, which is a classification, where our boundary, our orange line, is separating two categories, two distinct sets that are not numerical in value. Let's drill down a little bit more. We see that every dot here is an internet service provider, and each is represented on a 2D chart by two characteristics, the download speed and the upload speeds. Those are our inputs in the model. So we have two input features. However, we also see that there are different symbols for a class of slow ISPs and a class of fast ISPs. And the goal of the problem here, the classification problem, is to separate the slow ISPs from the fast ISPs. So what makes it a classification is the fact that the output space is not made of numbers, but it's made of categories. In this case, just two categories, slow and fast. These techniques have lots of applications in business. Here you see two examples of regression and classification. Regression, for example, applied to predicting the future value of an asset. In this case, the value is a price and is a number, and so it's a regression. And classification applied to the problem of rejecting spam. So for an incoming email or text message, the classifier, the model asks the question, is this spam or not spam, which are two distinct classes, and so it performs a binary classification. Here are a few other examples of supervised learning in business. Price prediction, where you may want to predict for the price of a house, but it could also be regressing the amount of sales you have, and trying to forecast how many sales you will do in the next quarter or in the next month. Regressing and predicting the number of downloads, predicting any number prediction is basically a regression. Classifying documents, this is also very common, where you have user-generated content, for example, and you need a system that kind of triages the documents into buckets that you know of. These could be topics, these could be types of documents, and so on. For example, a law firm could be interested in separating paid patents on a certain topic from patents on a different topic. A media outlet, a news source that receives comments from users may want to triage them by topic or by other characteristics of the text. And this is a document classification. Finally, the last example I put here, but it's by no means this list is exhaustive, is sentiment analysis, which is a very common technique where you the input to your model is a piece of text, and the output is a value that says whether the sentiment is positive or negative, which means whether that text describes some positive related feelings or negative related feelings. This is really relevant for a market. For example, if you have a website that receives reviews from your users, you may want to use sentiment analysis to score how positive or negative the feedback is from your user. And another example is if you have a very large social media page and a lot of people comment, you may want to aggregate their comments by polarity. And there are many applications of that. We can go into detail in the Q&A if you're interested. There are many other examples: image classification, text classification, forecasting, and so on. I just brought up three here because I think they're very important. What I want to stress is, or emphasize, is the fact that since we're dealing with supervised learning, what we mean by learning is we're hoping that the model is able to generalize from examples. Okay, so we don't want the model to learn by heart the data set we're using for training. What we want is that the model finds some rules or some patterns that are general enough so that when new data will come to the model, it will still be able to solve the task. For example, let's say we want to perform an image classification task that has the goal of separating images that contain cats from images that contain dogs. This we will prepare our data set with a bunch of we call labeled images, where for each image we have a ground truth label that says whether that image contains a cat or it contains a dog. And our model will receive these pairs of image label as inputs and outputs to the model. And it will learn some patterns. Hopefully, if the model has learned general enough patterns, it will be able to perform on new data with the same performance as it had on the training data. In order to verify that that's the case, what we typically do, we separate the data into two sets, a training set and a test set. Typically, we use 20% or 25% for the test set, but other choices are possible. And the procedure here is to use the data in the training set together with the labels corresponding to the training data to train the model, which means allow the model to learn the rules that connect the input to the output. And then what we do is we measure the performance on both the training set and the test set, and we compare the two. If the two performances are similar, that means our model is able to generalize to data that has not seen during training, and that is a good thing. So this concludes the very, very short introduction to machine learning. The next topic of today is deep learning. And I'm sure many of you have heard of deep learning before, and many of you are curious about deep learning. And I want to talk a little bit about what deep learning is and why everybody's so excited about it. Deep learning is not a new technique. It actually was invented over 50 years ago, but it became really famous and really popular in 2012. When there is a competition called the ImageNet Challenge, where researchers from all over the world, they compete on building models that solve an image classification task. The image classification task is to recognize objects out of 1,000 different categories in a data set of 1.2 million images. And up until 2012, machines were doing really, really badly. The typical error rate was about 25%, which means 1 image in 4 was classified incorrectly. In 2012, a team of scientists proposed a deep learning-based model which achieved a staggering performance of 16% error, which is much, much better than anyone had done in all the years before. This kind of started a revolution, and within 3 years, the error had become like below 5%, and that's the rate at which humans perform on this data set. And since then, there's been continuous improvement, and deep learning kind of exploded, and everybody's talking about it. So the first reason why deep learning became so popular is that it solved some long-standing machine learning problems in a very, very performant and accurate way. But it's not only that. Deep learning also allowed to solve problems that were previously quite more untractable. For example, you see on the right, the caption generation problem, where there is an input image and the output is a textual description. Now, this problem is still an input-output problem, which is a supervised learning problem, but the nature of the inputs and the nature of the output makes it hard to treat with other machine learning techniques, for example, a decision tree. Whereas neural networks, which is another name for deep learning, are very suitable to this kind of input-output pairs. Other successes of deep learning include speech recognition and speech synthesis, machine translation, which is translating from one language to another, medical diagnostic. Here you see a picture on the bottom left of the back of the eye, the retina. And there's been quite a lot of development in automated diagnosis of retinal disease, as well as automation and control. In particular, deep learning is extremely good at dealing with data that is so-called unstructured. This involves images, involves sound, it involves text, and pretty much any other type of data for which it's not trivial to see numerical features. So if you have data coming from a database, for example, your user behavior on the website, maybe deep learning is necessary, but maybe you can get away with traditional machine learning. On the other hand, if your data is of the types indicated here, the images, sound, text, or binaries of different sorts, where some feature engineering and feature extraction processes are necessary, then it's very likely that deep learning will help a lot solving your problem. There are two other reasons why deep learning became so popular. The first one is what we call the learning curve. This is the curve represented on the left, which compares the performance of a model as a function of the amount of training data available to that model. And what tends to happen with traditional machine learning models, for example, decision trees or logistic regression and others, is that they improve their performance as more data is given to them, but at some point they stop improving. It means the performance of the model has saturated. On the other hand, a large enough neural network will keep improving the more data it's given to it. So that makes it for very, very, very powerful technique. The other reason, which is represented on the right, is that deep learning allows to do this end-to-end machine learning between complex input-output pairs. The example that I gave before of the image to text is one such example. This is in contrast to traditional machine learning, where you have to do several steps, for example, extracting features and then applying a model after you've defined the features. These two reasons made deep learning really, really popular, and it's kind of exploding, and everybody's applying it to all sorts of problems. So how is a deep learning model built? A deep learning model is built in terms of units, which in the simplest example, which is the one we're seeing here, just perform a weighted average of their inputs. This seems pretty simple, and it's kind of weird why it becomes so powerful. The reason it becomes so powerful is that these units are actually repeated and connected many, many times to perform a very complex architecture. So if you look at this diagram from the left to the right, what you see is a set of input features. These are numbers that describe your input data. And each of them is going to multiple nodes in the first layer. So if we take the top node, it's receiving the input features, each of them mediated by a specific weight. You see here there is a weighted average, which means each feature is weighted, multiplied by a weight, and then added to the other weighted features and to a bias. So each of the nodes in the first layer performs that operation of a weighted average, and the weights going into each node are different. This makes it so that the output of each of the nodes in the first layer is going to be different because the weights of the inputs were different. Then the output goes through what's called an activation function, which is a nonlinear function. We'll talk a little bit more about these in a second. Basically, the output is mediated through, is passed through a nonlinearity, a nonlinear function, before it's fed as a new feature to the second layer. So the nodes in the second layer are receiving a weighted average, are calculating a weighted average of the outputs of the activation functions of the outputs of the layer number 1. And this process can be repeated indefinitely. So what makes a network deep is the number of layers and the number of nodes that go into the calculation. And then at the end, we have one final layer, which will have as many outputs as the ones we need to calculate, and will produce the answer that we want to compare with our labels. So the activation functions are where all of the power of the neural network lies. If they were not present, if the layers were simply feeding a linear combination into the next layer, the neural network would not be able to perform any better than a simple shallow model. The fact that there are these non-linearities makes the network able to draw very complex boundaries that can have all sorts of curves and turns. And this is what makes the network really powerful. So I realize this is going really fast, but given the time allowed, that's, I hope I give you some pointers, and that's the important thing. The next thing I want to talk about is different types of models that you may want to try when testing when approaching a new problem. This is a kind of a timeline, not complete, not exhaustive, of different models. And as you can see, neural networks are not one of the most recent models. They actually have been around for quite some time. However, one thing that distinguishes neural networks from other types of models is that they are really compute and data hungry. They require lots of data and lots of computing power. And that's why they were not used so much prior to the last 10 years, maybe, because we didn't have cheap compute and lots of data available. So what are the other options if you don't have lots of compute or don't have lots of data? My preferred method, my preferred model in that case is the decision tree or variants of decision tree, which could be random forest or gradient boosted trees. These methods, these models are really good in working with structured data. So data coming from a table, think of it as a CSV file, Excel, or a database. They require a lot less hand-holding or a lot less precautions than neural networks, and they are extremely fast, both to train and for inference. Other good models are the support vector machine, which was the most popular model before neural networks became famous a few years ago. And also, I want to mention the logistic regression, which is a simple model, but it turns out to work extremely well in some cases. And since it trains fast and it has a small memory footprint, I definitely give that a try when I approach a new problem. So in conclusion, when you're approaching a new problem, these are the kind of questions that you gotta ask. The first question you gotta ask is this a regression problem or a classification problem? Regression problems are the ones where you are trying to predict a number. On the other hand, classification problems are problems where you're trying to predict a class, okay? The second question you want to ask is, do I have input tabular data or input unstructured data? Is my input data images, sound, or text, which is unstructured, or is it a table coming from a database or an Excel spreadsheet? This will inform you in the kind of models that you may want to try first. The third question you may want to ask is, how many data points do I have? Given the fact that some models require more data than others, this may help you choose which models to try first. If you have little data, you may want to try tree-based models first, or simple models like logistic regression and linear regression. If you have lots of data, you may want to try neural networks or ensemble models like random forest, for example. Next question you want to ask is, how many features have I got? Have I got a few features and therefore I can try a simple model, or have I got lots of features and maybe some of them have complicated interdependencies and I want a more complex model that can capture those. Finally, the two very important questions you want to ask is how much computing power do I have and how much time? To give you an example, a project I worked on for a client, we used over 16 GPUs for several months to train our final model. And that's by no means a big amount of compute power in today's deep learning projects. So if all you have is your laptop, maybe deep learning is not the technique for you unless your data set is also small and can be treated on a laptop. If you have a GPU available, or if you have some cloud credits that you can use a GPU on any of the cloud providers, then deep learning becomes a lot more interesting, and you can start working on that. Finally, we are going to use Python. So I'll introduce briefly the libraries in Python that we're going to use. And I see that there are some questions, so I'll definitely tackle those at the end of the talk before we go into the labs. Here are the Python libraries that we are going to work with. Python is an amazing programming language. It's become the standard in data science because it's easy and powerful. And those two things make it a de facto choice in all data science, machine learning, and deep learning work. The libraries that we will introduce today are scikit-learn, which is a great library for beginners. It has lots of different models, and it's wonderful to tackle smaller size data sets and try out different models and compare their performance. For deep learning, we'll use a library called TensorFlow, and in particular, an API called Keras, which makes it really easy to define deep learning-based models. So we're about to transition to the coding part of the talk. I remind you the links are at ZTDL talks. Before we turn off the slides, I want to mention the bootcamp once again. If you like what you're seeing and are based in the Bay Area or can fly here, we have a bootcamp June 3 to 7. And for the participants of this talk, we have a discount code AICAM10 that you can also find on the slides. So let's transition to the code. But before we do so, let me take a look at the questions, if there is any questions.
Yeah, I think there are a couple of questions. You can take a look.
Yes, okay. Okay, so first question, bit.ly, it's bit.ly/ZTDL talks. Voice input from human and output as computer voice. That's probably not necessarily a machine learning problem. You can probably get away with simple sound processing. So if you want just the voice to sound like a computer voice, you can just do some signal processing technique. However, if you want to really do it with machine learning, what my recommendation would be is to go through an API that allows you to convert the voice to text, and there are many such APIs that are available, and then use a speech synthesizer to reconvert the text to speech. Okay, more learning events. Okay, an example of big and little data sets. By today's standard, anything lower than a few gigabytes is considered a small data set, whereas anything larger than few gigabytes is considered medium size, but for large data sets, I would say probably like hundreds of gigabytes or terabytes in terms of disk space. In terms of examples, I think the threshold has really to do with the complexity of the problem, not just with the number of data points. but pretty much, you know, if you have a few thousand data points, I would definitely give decision trees first a try. If you start to have like tens of thousands or even millions of data points, that's where, you know, neural networks become more interesting. GPUs, what are GPUs? That's for graphical processing units, and it's basically the graphics chip in many computers. Some of them are general purpose, meaning they not only manage the graphic, but also they manage, they can do calculation, and they have been used for automating deep learning work. At what level do I have to be skilled before diving into deep learning? That really depends on where you come from. If you're a software engineer and you know Python, I think you can get started right away. If you don't have a software engineering background, then I would recommend getting some solid coding background, as well as you know, understanding linear algebra, at least as far as you know, matrices, vectors, matrix multiplications, and all that. Training of neural networks, is there a methodology followed when it comes to selecting which layers are present, or the process of trial and error? Yeah. So there is, unfortunately, this is a question I get a lot, and unfortunately there is no method that allows you to choose the exact number of layers and nodes. So it is treated as a trial and error. Technically speaking, this is called a hyperparameter search problem, which is basically another machine learning problem. So you do see efforts of applying machine learning to solving the problem of configuring your machine learning model. This is kind of like convoluted, but it's actually simpler than it is. Most of the time, it's a random search, meaning you literally try random sizes for your layers and your number of layers and see which one works best. The good news for you is that most of the problems that happen in business have been explored by some academics. And so if you look for a paper that has explored your problem, you may find what the best architecture is for the problem you're trying to solve. Suggest a way to convert own database of many PDF into words. You can use any OCR technology. Tesseract is a free and open source one, but there are many other ones. OCR stands for optical character recognition, and that's what you're looking for. Difference between machine learning and deep learning, that's a very good question. Deep learning is a branch of machine learning. So machine learning itself is a branch of AI, artificial intelligence, that has to do with learning from examples and from data, rather than other AI techniques which are based on logic and writing rules. And deep learning is one subcategory of machine learning that uses neural networks as models. The link, again, I'll post it here in the chat, is bit.ly ZTDL talk. Okay. I think it should be good. Make a brain in n dimension with that words. Maybe we can turn automatically answer for the problem. I didn't understand that question by Jackson. If you can rephrase it. Okay. GTX 1070 is actually a very good GPU for starting point. So you will have to measure it on your problem and see if it's good enough. But it's I know a lot of people who use that. Definitely GPU for machine learning, between GPU and FPGA. FPGAs, I've not seen many people using them. It's not clear what advantage they bring to the table. GPUs are a well-tested technology. Okay, so deployment versus training. The question is, I mentioned a model that can take months to train, but once it's trained, what's the performance in deployment? That's a very good question. The model that took months to train could, work in sub-second inference time. It depends on where you deploy it to and what operations you do to make it go faster when you deploy it. It fundamentally, this is related to the model size, meaning the number of layers and nodes, aka the number of weights in the model, and there are many techniques to basically trim this down to the core and make it go much faster. So when you design a model, one of the considerations you will take into account is also deployment, meaning if you have requirements and constraints in deployment, you'll need to choose a model that fits those requirements. For example, if you're deploying a model to serve advertisement and that the model needs to work at sub-millisecond inference time, because you don't want the user to wait for the ad recommendation. Whereas if your model is working on batch images and nobody's waiting for the model to give an answer, it could very well take a few seconds for each prediction, and it doesn't really matter. So you need to take that into account. Last question, because I then want to review the code. How do we start when we know a problem and we solve it but not have data? Okay. Then you need to collect the data. If you don't have labels, let's treat the two categories. You don't have data or you don't have labeled data. If you don't have data, then you just need to set up your collection pipeline so that you start collecting the data. And if you're in that situation, you might as well try to set it up in a way that you collect the labels as well. However, if you have data but you don't have the labels, then really that's where it becomes costly. You will need to have humans to review your data and label it. And there is no really any way around it. There are efforts in automated and unsupervised machine learning that basically requires no data. But I think none has become mainstream yet. There is obviously a lot of interest in those methods because a lot of people are in that situation where you have lots of data, but you don't have the labels. But as of today, the best thing you can do is just get some human labelers. And there are services like, for example, Figure 8 that allow you to pay people to label your data. Effective ways to cut the time and CPU power required when using neural networks. It's a very vast topic. I encourage you to take a look at TensorFlow. There is a whole section of the documentation about deployment, and they talk about that. If you use I'm not sure about this question. So I'll yeah, Jackson, I'm sorry, I'm not sure what you are asking me. So I'll go ahead on the code, and if you want to rephrase that. Okay, so let's share. Okay, so this is the talk links, the slides. I hope you'll find them. There are two notebooks that are linked here, the scikit-learn notebook and the Keras notebook. I want to point out, these are Jupyter notebooks. If you're not familiar with Jupyter notebooks, then you should go and read the introduction documentation of Jupyter. It's basically an environment where you can execute code as well as type text, and it's become really popular in data science, machine learning, and deep learning. So what we do in this first notebook is we load data into what's called the pandas data frame, which is a data structure for tabular data, and inspect this data. We look at, there are 5 different columns. You see it's like an Excel spreadsheet with numbers. Of these columns, we will use the target column as our label. This is a binary label with 0 and 1. And we'll use the other columns as features. So one thing you may notice is that there is one feature which is categorical. It has letters here. And so before we actually go ahead and feed these into a model, we need to convert these into numbers. And the simplest way of doing it is to do what's called one-hot encoding, which is creating 3 dummy columns that are 0 or 1, depending on what the original value of the source was. And then what we do is we perform a train test split, which is splitting both the features, which traditionally are called X with a capital letter, and the labels, Y, into training and test set. The difference between Jupyter Notebook and Colab is they are the same. Colab is hosted on Google and it's free to use. So I definitely encourage you to use Colab for trying things out. Jupyter is self-hosted. The files, I'm not sure they're exchangeable. I think you can export from Colab to Jupyter, but no, yeah, actually they are. Yeah, you can totally load from Jupyter into Colab, and you can even open GitHub repos. So yeah, I would use Colab for basically prototyping. It's good. It gives you a free GPU. You can go ahead with that. Jupyter Notebook is the project Colab stems from, and it's self-hosted, so you can run it on your machine. Okay, back to training test. We've split the data and the features and labels into train and test. And here is where we do the machine learning. This cell is the machine learning cell where we import from scikit-learn in the tree submodule, we import a decision tree classifier. And this is one of the wonderful things about scikit. All the models have the same structure. So you initialize a model by creating an instance of that class, and then you run model.fit on the training features and the training labels. This is amazing because, for example, if I wanted to train a different model, for example, a logistic regression, what I could do is, instead of importing the decision tree classifier, I could import from linear model, import the logistic regression model. And now I just need to change my model into a logistic regression. And as you can see, the rest of the code just works just fine. So you should explore what models are available in scikit-learn and basically try to swap them and see which one works best. Once you have trained your model, which in this case, it's an instantaneous training, as you see, the cell returns immediately. The model has learned what it could learn from your training data. And what you can do is measure the accuracy or other metrics, for example, here the confusion matrix, on your test data. And if you want, you can compare it with your training data. Some models allow you to explore the feature importances. For example, tree-based models are very good at doing that. And here we can see that some features are more relevant than others. And you can also display a decision boundary. There is an exercise that you can use to explore the properties of these models, and I'll let you do it in your own time. The other notebook I want to explore, which in the slides is linked as Kara's notebook, in the gist is linked as Kara's notebook, is a notebook that introduces how to build neural network models using Keras. The data is the same as before. We have input and output features. And here we build a model using Keras. Now, this is a bit more complicated than model building in scikit-learn. Model building in scikit-learn was just a one-liner here. And here you see it's a few more lines. We specified the kind of model we want to build. In this case, it's a sequential model. And in the sequential model, we define how many layers we want to insert. In this case, we have just a single layer with the output. This is because it's a shallow model. But if you scroll down, here is a different model where we have three layers. We have a first layer with 4 nodes, and this receives the 2 inputs, and then a second layer with 4 nodes, and then a final layer with our output. Notice that the layers all carry an activation function, in this case, hyperbolic tangent, and we can change that to whatever we like. The important thing is that since this is a binary classification, aka the labels are only 0 and 1, the output has a single node whose activation is a sigmoid, which will predict the probability between 0 and 1 of the output. Once we have defined the model using the sequential API from Keras, the next step we gotta do is to compile the model, which means specifying which loss function we are going to minimize, which algorithm we are going to use to minimize the loss. In this case, it's stochastic gradient descent, and there are many others, as well as if we want to keep track of any other metric, for example, the accuracy. Once we have done these 2 steps, which I agree, they're a bit more complex than the one-liner here, what happens is the same. We fit the model on the training data and the training features. Training in deep learning is an iterative process, so we specify the number of iterations we want to do, in this case 20. And once the model has finished training, you can see how the loss decreased, that's a good thing, and how the accuracy improved both on the training set and what's called the validation set. Same metrics as the ones we had before. Here you see the training score, the test score, as well as the confusion matrix, and a very nice decision boundary that is curved around the data we wanted to separate. Both of these notebooks come from our BOOTCAMP repo that is available and open source, and you can play with it. I'm going to open it on GitHub and then comment a little bit on that. Yes, so this is the repository. All of the instructions are provided here for how to run the code, how to create the environment, and how to troubleshoot if you have any problems. So, feel free to clone it, fork it, star it. Please give us a star. We always appreciate that. And play with the code. If you have any questions, come back to us. We'll be happy to help. And yes, if there are any other questions, I'm happy to answer. Otherwise, this is probably concluding our time. And see, there is one more question. Could you post the script link of the Jupyter notebook here? Which script link? This one? If that was not the link you were looking for, then let me know. How to get to the bootcamp material. Okay, I'll add a separate link right now, and maybe I'll stop sharing my screen. 1 second. I'll add a link on the gist with the bootcamp. Oh, actually, yeah.